Block diagrams are a convenient way of representing systems using transfer functions. This should be familiar from 435. A block diagram looks like this. It has an input, an output, and it is some transfer function where g of s can be written as a ratio of two polynomials n of s and d of s. The input is u, the output x. So this can be written as x over u. I'm going to show four typical blocks. First is a constant where g of s is a constant. In this case, x, the output, is k times u, and x. You can see the transfer function follows directly. X over u is equal to k, which is my transfer function. The next is a general transfer function. In this case, the output is equal to the transfer function times u. Another common block is called an integrator, 1 over s x. So x is equal to 1 over s u. That's not so obvious, but if we rewrite this, we would write s x is equal to u. Remember that in our simplified Laplace transform system, we replace the derivative with a power of s. So this could be written as derivative of x with respect to time is equal to u, or the output x is the integral of u dt. Hence this is called an integrator, and it is a fairly common block in control systems. The final block is a summation block, and it's a way of combining multiple inputs, and it looks like this. u1, u2, output is x. In this case, x is equal to u1 plus u2. Now, I have just used summations here, but these could be different signs, and then it would change this right here. The advantage of block diagrams is that you can use them to model parts of a system and then connect the block diagrams together according to the functionality of the system. This gives you a larger system composed of many block diagrams. Combine all the block diagrams into a single larger block, which is a differential equation, and then use that differential equation to analyze the system. Here's an example of using block diagrams. My physical system is this. Two masses connected by a spring. The input is a user-applied force. I'm interested in the output of mass 2. I can model each of these pieces, the mass, the spring, and the mass, with a differential equation. I begin by breaking my system into pieces and drawing the free body diagram for each piece. Force, spring. Now I can write F minus Fk is equal to m1 x1 double dot. Fk is equal to k x1 minus x2. Fk is equal to m2 x2 double dot. I'm now going to write the transfer function for each of my three components. The first one, f minus fk is equal to m1 x double dot 1. The input is f minus fk. The output is the position x1. So if I write this in Laplace in the transfer function form, I have f minus fk is equal to m1 s squared x1. Notice that I'm being sloppy in the notation. F, fk, and x are all functions of time. Once I take the Laplace, they're now functions of the Laplace variable s, but I have not changed the notation. You were to assume if you see s in the equation that it's a Laplace equation and the corresponding variables are functions of the Laplace. Now write the transfer function. X1 over f minus fk is equal to 1 over m1 s squared. Next, input fk is equal to k x1 minus x2. The input for this system is the force Fk. The output is the spring deflection, which is x1 minus x2. And so with some quick algebra, I have that the transfer function x1 minus x2 over Fk is equal to 1 over k. Because there's no derivatives in this system, this is just a linear relationship. I could also write this as fk over x1 minus x2 is equal to k. The third piece, f Fk is equal to m2 x2 double dot. We can write as transfer function x2 over f2 is equal to 1 over m2 s squared. Next, I'm going to put these systems as block diagrams. Now, I know the answer here, so I'm going to write this in a way that turns out to be convenient so that my lines end up being nice. 1 over m1 s squared, the input, f minus fk, the output, x1. That was our first component. The second component, k, input, x1 minus x2, output, fk. Third component, 1 over m2 s squared, input fk, output x2. At this point, I've taken my original system, I've broken it into smaller pieces that I can model as transfer functions. Then I've written the blocks for each of those smaller pieces. Now I need to connect the input-output relations. As I said before, I've cheated a little here because I know what the answer is going to be. And so instead of drawing it arbitrarily and then rearranging the blocks so it turns out neat, I've drawn them into positions and orientations that's going to work out well in the end. So let's just connect up the inputs and outputs. The input to my system is f. I need to generate f minus fk. There's f, here's fk. So I subtract that one, add that one, and I get f minus fk. On this set, I need x1 minus x2. I can create that by taking the output x2, x1, and subtracting the output x2. Finally, all I need is fk here, so I can pull that off like that. The output for my system, I'll pick right here, x2. I now have a block diagram for my 2-mass spring system that I've built up using smaller block diagrams from the individual components. The next step would be to find the total system response from f to x2 by combining all these blocks. And next we'll look at two ways of doing that, one using block diagram algebra and one using what I'm calling the brute force method.